I think that the problem here is that it's completely backwards from the way that all the other ones are, right? All the other ones, they give you a common ratio, they give you a starting point, you add it up, and you get the answer. Here they give you the answer, and they want you to come up with all of the other stuff, at least so it seems. So let me copy this down, this particular version at least, and let's see, 7 in, a is equal to 41, and this is n equals 1 to infinity. And this hopefully will end up helping with the other problems, but we can go back and we can talk about some of the other problems as well, if need be. So when I look at this, well, at first I was like, wow, that's a hard one. And then I realized, it's not that hard when you actually think about it carefully. So we're supposed to solve for x. So solve for x. And the way we're going to do this is we take this thing over here and we ask ourselves, is that a geometric series? It is. It is geometric. Whoops, why did I do a G there? I don't know. Geometric. If it is geometric, it must have a starting point. And it must have a common ratio. So it might be helpful if I rewrote this just slightly. So notice that if I write it like that, it makes it a little bit more obvious that, and actually I could even write it like this, 6x to the 7th, and then 6x to the 7th squared, 6x to the 7th cubed. Anyway, that's what we're dealing with here. We have the first term when you plug in equals 1 into this, or that up there, you get 6x to the 7th. When you plug in equals 2 into that up there, you get 6x to the 14th, which is the same as 6x to the 7th squared. So each of these terms, the common ratio is x to the 7th. So we have x to the 7th for the common ratio. The starting point, now that I've written this here, of this summation, which if I change the commas to pluses, then I have that series. Whoops. There. The starting point is 6x to the 7th. And the formula is the starting point. And I know that if you look this up online, they'll use letters like A for the starting point, and they'll use R for the common ratio. In fact, I think I'll just use R for the common ratio here. But I like to emphasize that we're doing the starting point. It doesn't matter what n is in terms of as long as it's a geometric series, starting point. So you take the starting point, multiply it by 1 over 1 minus the common ratio, and you'll get the overall sum for an infinite series that's geometric. So let's do that here. 6x to the 7th times 1 over 1 minus this common ratio. So all I've done is I've taken that up there, and you can just substitute whatever numbers you had. So you get a similar thing. And that gives me 6x to the 7th over 1 minus x to the 7th. And what is it that this was supposed to equal? Oh, it's supposed to equal 41. All right, this can't be that hard. Let's do this. 6x to the 7th is equal to 41 minus 41x to the 7th. That means 47x to the 7th is equal to 41. Okay, so this isn't all that great. X to the 7th is 41 over 47. Wow, this is terrible. Did I make a mistake somewhere? I don't know. We're going to find out. So x is equal to the 7th root of 41/47. Surely that can't be the answer, because at least one of you texted me or emailed me, and I looked at it, and I was like, that's going to be not bad. Let's see. What does it give me here? Just a second. Oh, yeah. Guess it is. Let me see. Oh, it'll let me. Let me do this. Let me do it on here. So the 7th root, is it the 7th root? Yes, 7th root of 41 all over 47. Let's see if this is correct. Oh, it is right. Okay, so you could do the decimal if you want. Yeah, someone else had their answer, and it was like the answer was 1/3 or something. I forget. Someone was much more fortunate than me. So I thought that they might all work out nicely, But whatever, this one's not bad, is it? Now that we see how it works. So there it is. That's the last one. 8, 7, whatever it was. Here's my work again. Do you have any questions about that one? And then we'll go back and see if you have questions about any of the others. That one wasn't, now that we see, what do you think, Cooper?
You only use that 1 over 1 minus r for infinite.
Yeah, if it's infinite. Yeah, if you have a geometric series that stops somewhere, then you do 1 minus the common ratio to the number of terms over 1 minus r. So yeah, I know. You could look up these formulas, and they would have it all in terms of with letters. But I like to just remember it's the first term times 1 over 1 minus the common ratio. But yeah, that one's going to be, we're going to use that a lot. That is going to be a common thing. And by the way, this only works, so this is super important, is that geometric, in fact, this will be my first slide for today. Geometric series converges when r is between -1 and 1, and it diverges otherwise. So, in other words, if I have a geometric series that looks like this, 5 times 4/3 to the n, and goes from 1 to infinity, then that diverges. In other words, that, because if you think about it, 4/3 to the n, you're adding up 4/3 plus 16/9 plus 64/27, and so on and so forth. The numbers here are getting bigger and bigger, and so of course, if you're adding bigger and bigger numbers, it's never gonna, you're always gonna, it's just gonna go to infinity. So, I think you had a couple like that on your homework though. So, getting back to the homework, were there other questions about either this problem or any other homeworks that you had trouble with? Let me just, so that you have full disclosure, on your quiz, I have 3 geometric series. You just have to tell me, does it converge or diverge? And if it converges, tell me the sum. Infinite geometry. So if you remember, first term, 1 over 1 minus the common ratio, you're going to be good. Now everyone's like, oh, that's easy, let's do it. Everyone's like, okay, packing up, let's go home. No, we got another 45 minutes, we can do this. Okay, yeah, let's do it. We'll do this now, and then we'll, I'll move on to something new. Maybe through here, and I'll do this group wants 4. See if that's 4. Enjoy. Is that enough? That's enough. Amazing. Actually counted correctly. All right. So it's all working. It's the quiz. This is one of those situations where you should be able to do these pretty quickly, and it will help you in the long run. Kind of like when you learn derivatives, you remember that? Took a while at first, but now you can do derivatives like that. So hopefully you can just look at these and say, this is geometric, and this is the way it's going to go. So I'll give you another minute or so, but try to get through these. I see some of you are already done. You want me to check my work against yours, which I'm happy to do. And this. Interesting. It's all coming in now. Oh, super quick. Good job. It's okay. You got a question mark there. You hope. Okay. I never know what to do with question marks. Very good. Yeah, if you don't want to simplify that last one, that's fine. You can put the old going here. Yeah, just put your numbers in. And now I'm making your choice. You're doing it right. You got it right. You just got to put that last number. Put it there. Just write it there. Nice work. Good job. See, I knew you could do it. Good job. I know, I'm making everyone tense. Okay, I think I got them all now. Anyone else want me to stand over you? Okay, no one else has one. Good, good, good. So, stapled together. So let's look at mine. Hopefully you got the same thing as me. Most of you did, so super encouraging. So here's what I got on the first one. So looking at this, I just talked through this. Some of you didn't get the same as me, but you were pretty close. Even if you think you weren't close, I'm probably going to just take off like a half a point because you were really close. So here I've got a sum common ratio. This is, so first of all, I recognize this is geometric, and this common ratio is 10/11ths. So that's the first thing I note. And then I want the starting point. The starting point is the first number in the series. So the first number in the series is going to be this to the first power, which is just that. Now I put it into my formula. The sum is the starting point times 1 over 1 minus the ratio. Some of you had the starting point as 1, which you got a different answer, but it was, if you got 11, or whatever, what would you get? Yeah, you might get 11/10 or something, I don't know. Whatever you got, I'm probably going to be reasonably happy with because you just messed up the starting point. So anyway, there it is. 10 is the final answer there. The next one, I think almost everyone, if not everyone, got this one right. This one is pretty straightforward. You look at this geometric and you say, okay, what is the common ratio? The common ratio is 5/3. 5/3 is bigger than 1. Diverge. Diverges. This is beautiful. The last one, I know you had to do some arithmetic here, or you could have just boxed this, and I probably would be happy with it. But here again, common ratio. What is the common ratio? It's -3/5. -3/5 is between -1 and +1, so we're okay. Then we figure out the starting point. The starting point is the very first number in this series. So plug 1 into this, and I get -3/5 to the 0, which is just 1, which is confusing, I know, but there it is. So the sum is going to be 1 times all that mess, and if you didn't do the simplification right, at least you got this part correct. And so I'm going to be super happy, and probably everyone's going to get an A on this, but I know I got 100%. So I'm just going to put that up there to make myself feel better. Okay, so what we're doing today is I want to give you other series, and we want to figure out whether or not these other series, if they converge or diverge. So here's the game we're playing. I've got PowerPoint. We'll go to the PowerPoint in a minute, but here's the thing. This is it. Converge or diverge. That is what I want to know. Do these series, do they converge or do they diverge? So let me write down a few series for you. Any1 to infinity of 1/2 to the n. And then here's this one, n equals 1 to infinity of 2 to the n. There, just for fun. Give me a minute. I've got a few more for you. One more. Oh, whoops. Look at this. Let me just scrunch these up a little bit so that we have more room. There we go. Push that up there. In fact, I'll just copy that one. We'll do one more here. How about that one? And squared. There. Okay, so there's 4 series, 4 summations. In fact, I can write down the numbers so that you know what they look like. This is going to be 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. Remember, this game, I only want to know, does it converge or does it diverge? And explain why. This next one, we have 1, no, there isn't a 1 here. Give me a sec. This is going to be 2 plus 4 plus 8 plus 16, and so on. This next one is going to be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. You get the picture, don't you? This last one, 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, 1 over 25. I think you get the picture. So, the first two, you know the answer to, don't you? You know the answer. Let's get those answers. So let's do the first two, because I know that all of you know the answers to the first two. And then we'll talk about the second two. The second two, you're going to guess. So I know you don't know the answer yet. Maybe some of you do. It doesn't matter. We're going to just take guesses. So, first of all, the first one, Jackson, that first one, I'm going to label these so that we can talk about them. A, does A converge or diverge?
Converge.
How do you know?
The converge is between -1 and 1.
This is geometric. and the common ratio is 1/2, and 1/2 is between -1 and 1. That was a beautiful description of why this converges. Now, you could compute what it converges to, but right now, at least for the time being, all I care about for the next few weeks is, does it converge or does it diverge? That's the game we're going to play for at least the time being. Okay, the next one. Andrew, what about letter B? Does B converge or diverge?
It diverges
It diverges? How do you know?
because the ratio is greater than 1.
Okay, so the ratio is 2 in this case, and so 2 is bigger than 1, so this diverges. Diverge. This one converge. By the way, you're going to be tempted. In fact, my Calc 1 students, I think they were the ones, they're a little bit more talkative than you, and they were telling me before class that they can cheat on the homework, and they explained to me how they cheated on the homework, and I said, yeah, you can cheat on the homework, but you're just cheating yourself. So let me explain how you can cheat on the homework. With these questions that ask you, does it converge or diverge, you get 3 tries, don't you? Well, there's only 2 answers. So pick one of them, click submit, and if you get it wrong, pick the other one. That's the lazy person way to do this. Better to actually think about it, choose your answer, and then if you get it wrong, you know you can get it right, but actually try to figure out why you got it wrong. So don't just guess and get it wrong, although I am going to ask you to guess with these last 2. So let's do C and D really quick. C. In fact, why don't you jot down somewhere for C and D, do you think these converge or diverge? Those 2 right there. 1/1 plus 1/2. By the way, this one here, check this out. You get 1/100 at some point. You're going to have 1/1,000,000. These numbers are really small. They're super small numbers. So, I mean, you keep going, though. You're plus ... So does that converge or diverge? And then after you guess this one, what about that one? Those numbers get really small as well. I should probably have one more. Just a minute. Oh, yes, I've got a good one. Sorry, I've got a letter E. We're going to have to move this geometric series nonsense. Oh, wait, I can move all of this up. Hold on. Here we go. Move this up. Yeah, I should have had another one ahead of time. This is why I should stick with the PowerPoint. But I know what's coming with the PowerPoint. Let's do a letter E. This one should have come before C and D, by the way. So just pretend that you're doing this before C and D. Let's do n equals 1 to infinity of n squared minus n over n squared plus 1. Let's do that. So what's this look like? It looks like this. 0. It's starting out nicely, isn't it? A 0 there. Okay, plus, give me a sec here. This is going to be 2/5. And then the next one is going to be 6/8. And then the next number, I'm just plugging in the numbers. This is when I plug 1 into this. This is what I get when I plug 2 into this. 3. And then let's do one more number, and then we'll put some dots. So if I plug 4 into this, I get 12/15. And then I'll put some dots. So take a guess about letter E. Does E converge or diverge? Okay. Now that you've got your guesses, let's talk about these 2, C, D, and E, or these 3. I guess I think of them as 2 because C and D are really similar, aren't they? So let's talk about those 3. What do you notice about, does anyone notice anything special about letter E that's not true about C and D? Oh, what do you think, Connor?
The numbers continue to get larger.
Ooh, they're getting larger. So do you think that's going to converge or diverge?
I'd say diverge.
Yeah, this one is actually going to diverge. So this brings up the first test that we can do for convergence. And this is, so we've already got geometric series. That's going to be our first test. And then the second one is going to be the test for divergence. Test for divergence. This is also called the nth term test. Yeah, eventually, someday, maybe tomorrow, I'll pull up the PowerPoint. But I'm just on a roll here. I love this particular topic because it's like solving a puzzle. It's like solving the Rubik's Cube. You have to figure out where to twist it, and you're like, okay, I've done that part. Now I've got to do the next part. So each one of these is like another little algorithm or another little move that we're going to make. So the first thing that we made was the geometric series. If we know something's geometric, we're done. We can say for sure whether it converges or diverges. Now, if you don't have a geometric series, your next move is to do what's called the test for divergence, or sometimes referred to as the nth term test. I personally prefer referring to it as the test for divergence because that's really what it does. So here's what the test for divergence says. It says if the limit as n approaches infinity of a sub n is anything other than 0, then the summation diverges. So that's all it says. Now, check this out. Let's go back just to review. I mean, it's a pretty simple thing to jot down. I'll come back to this, though, because one of the things we're going to be doing over the next couple of weeks is we're going to be developing this long list. It's going to be dizzying, but you're going to have the geometric. We're going to review that one over and over again. Geometric series converge. Then we're going to have this test for divergence. That's the second test that you've got to remember. So we've got that one. The next one we're actually going to do today is called the integral test. And then, I don't know if it's today or on Friday. We'll see how long it takes. We'll get to the P-series test. So many tests. That's just 4 in just a week. We're going to have probably a dozen such tests eventually. But don't worry, we're going to take it one at a time, and each one of them builds on the others. They're not bad. Test for divergence. This is also called the nth term test. Let's go up here and apply this to these. I know, you already know that these converge or diverge, but let's do the nth term test, the test for divergence. So to do the test for divergence, you do this. You do the limit as n approaches infinity of the term. I'm going to do the same thing up here. Limit as n approaches infinity of 2 to the n. So notice that I just take whatever's written there and I do the limit as n approaches infinity. This is a limit that you can all do. It's not too difficult. Let's see if we can just pick a rando. Gavin, what is the limit as n approaches infinity of 1/2 to the n?
0.
It is 0. You get smaller and smaller. This goes to 0. Very nice. Gavin, can you hear me okay? You sure? You've got both of your ears are wide open. What about that one? Yeah, but it still shouldn't be there because it bothers me. Sorry, I know. I'm such a stickler, and I'm old. I'm too old for this. I know you guys walk around with those things. I always wonder when I see people talking to each other and they've got the earbuds in, what are they doing? Yeah, I can't do that. I always have to, the moment my wife walks into, if I have earbuds in, I pull them out. If she walks into the kitchen or something, I don't want her to have to look at me like that. But yeah, thank you. Sorry to, but I just, it's me. It's not you, it's me. Okay, next one. But you did a great job, Gavin. Onward, Luke. What is the limit as n approaches infinity of 2 to the n? It is infinity. Okay, now let's go back to the nth term test, or the test for divergence. Test for divergence says if this is not 0, which it isn't 0 here, then you diverge for sure. So this one for sure diverges. I know, we knew it already, but this says. Now here's the difficult thing that you're going to have with the test for divergence. And that is that if you get a limit that does equal 0, what do we know? We know nothing. That's the problem. And it's going to be tempting to turn that around and say that, oh, it's going to converge. Here, let's go back here and see what the test for divergence says. It says if the limit is non-zero, you diverge. This doesn't say anything about when the limit equals 0. It only says that if the limit doesn't equal 0, you diverge. Okay, so let's take a look at these two. Let's see. What is the limit as n approaches infinity of 1 over n? So we'll pick another person. Madison, do you know what that limit is? It is 0. Very good. So where are we? We're just going to pick Drew. Drew, what does that say? Does this sum converge or diverge? Wrong. Remember, this limit, if the limit equals 0, we don't know. So very good. Thank you for doing that. I appreciate him taking one for the team. Maybe I should write this down just to emphasize. If the limit as n approaches infinity of a sub n is equal to 0, then we don't know. And I'll put in parentheses yet, because we're going to know. So I was kind of hoping that Drew would say, I don't know, and I would say, you're right, you don't know. So anyway, let's get back here. So if the limit equals 0 of the nth term, then we don't know. So we don't know. I'll put a little question mark here. So this one for sure diverges, diverge. This one we didn't know, but this one happens to be geometric, so we do know. I'm just putting a question mark there just to sort of emphasize. Okay, next one. What about this one? Limit as n approaches infinity of 1 over n squared. What does this equal? Claire, what is the limit as n approaches infinity of 1 over n squared? It is 0. Caden, does this series converge or diverge? Excellent! That's the perfect answer. He shrugged and said, I don't know. Didn't even verbalize it. It was all mouth closed. Okay, don't know. Okay, very nice. So we don't know yet. We don't know yet. We're going to find out soon. What about this one? Last one, and then we're going to get to the PowerPoint, I promise. Eli, what do you think of the limit as n approaches infinity of this thing? It's going to take me longer to write it down than is for you to do it. All right. So Eli, what do you think of that limit? That equals 1. Okay, let's see. Now let's see if you were paying attention. Rachel P. over here. Does this series converge or diverge? It diverges for sure, because 1 does not equal 0. And so this one diverges. We don't have to do any more work. So that's the beauty of the test for divergence, is that you can tell if something diverges. And once you know it diverges, set it aside. You don't have to do any more work. You're done. Let's go back to these two here, because these are interesting. That one is so interesting that it has a special name. That one is called the harmonic series. That's a harmonic series. It is the harmonic series. Now I can pull up the PowerPoint. Hold on a sec. It's here somewhere. I know, I've got it. I just didn't use it. Hold on a minute. That's not it. That's for the other class. Why is that up there? Okay, is that gone now? Let me switch gears. I had it here, and now it's disappeared. Series. Is this it? I'm so sick of it. He's leaving it. Where is my harmonic series? Here it is. This is the harmonic series. This is the harmonic series. So, here's the interesting thing about the harmonic series. The harmonic series does not converge. It actually diverges. And it's really surprising. If you actually work this out, like I've done this, I've had my computer calculate the sum of the first billion terms of the harmonic series. That is, you go out to 1 over 1 billion, and you know what you get when you add up all of those terms, a billion terms? You get the number 7. You get something so small. How could this diverge? How in the world is this divergent? Well, here's how we figure out that this actually diverges. I'm going to compute partial sums. That is, I'll start with this one, just 1 and 1/2. So a partial sum is just what you get when you stop adding up after a particular point. So we start with this one, 1 plus 1/2. That's not too bad. I can do that in my head, but I'm not going to. The next one I'm going to compare this with is this one, S sub 4, which is 1 plus 1/2 plus 1/3 plus 1/4. But notice that what I've done here is I've grouped these. And the reason I've grouped them is because I want to emphasize that that stuff there, 1/3 plus 1/4, is actually bigger than if I change this to 1/4. So check it out. Here's what happens. If you change that to a 1/4, you get something smaller. So this thing here is bigger than this. And that thing I can compute. So this is 3/2, isn't it? It's 1.5. This is 1 plus 1/2 plus another half. This is 2. Because it's, so whatever I get when I cut this off right here, I'll get something bigger than 2. Bear with me. This is where things get exciting. Let's do S sub 8, the partial sum. Okay, very nice. Okay. Here's the partial sum S sub 8, and here I'm going to do the same trick. I get 1 plus 1/2 plus that stuff, but I'm going to change the 1/3 to 1/4. It makes the whole thing smaller, which means this is bigger than this. And I'm going to change all of those to 1/8. And so this is bigger than this. Now that sum is 1 plus 1/2 plus 1/2 plus 1/2. Hopefully you see where I'm going with this, but just in case, I'm going to do one more. Yeah, by the way, this is 2.5. I know, we're getting bigger, but not very quickly. The next one, oh yeah, there it is, 1 plus 3/2, very nice. The next one, S sub 16, if I take 1 plus 1/2 plus this stuff, plus this stuff, plus this stuff, and do the same trick, change the 1, because, by the way, this is 1/2 because you have 4/8. So here you have the same 4/8. Here I have 8/16. So 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2. If I add up all of that, I get 1 plus 4/2. Notice what's happening. Each one of these partial sums is getting bigger. It's going very slowly. If I did the next partial sum, it would be bigger than 1 plus 5/2, and so on. But the thing that is interesting here is that, 1 plus 5/2, of course, is that these sums, they get bigger. It's very slowly, but they keep getting bigger. So you might say, well, when will you have a partial sum that is bigger than 10, for example? Well, you could figure it out. You just have to figure out how many 1/2s you have to add, and then that'll give you the power of 2 that you have to go to figure out. So I guess 10 is 1 plus 16/2. 1 plus 16/2, so I'd have to go to 2 to the 16th. That's how far the partial sum would have to get for me to get to 10. But eventually you'll get to every number. It gets bigger and bigger forever. And so this thing does diverge. So S64. Oh, now that's a little bit of a mess there. I don't know why. But the harmonic series does diverge, is the important thing. And it turns out any multiple of the harmonic series diverges as well. So getting back to this, the thing that we need to remember is that the harmonic series and all of its friends, they all diverge. So this thing diverges. So maybe I'll put that on my list. You know what I'm going to do is I need to make this list. I do have a list somewhere. Oh, hey, whoa. Okay, let's go with one at a time here. Connor first, and then we'll get Jackson.
So one thing I was realizing as I was looking at that, I realized because the integral of 1 over x is a log function, the area underneath that curve is going to go to infinity as x approaches infinity, which means that the sum is going to diverge.
I think you should just teach the rest of the lesson, because that's the next thing that I was going to do. So, Jackson, we'll get to that is a beautiful statement. Jackson?
It's not quite that smart, but...
You want to take over as well? No, go ahead. Nice. Yeah.
Basically, just the reason why you turned all those groups into one map, it just keep things simpler.
Yeah, to make it nice and simple. And because I don't know what 1/3 plus 1/4 plus 1/5 plus 1/6 is, but I can say that when I add all those up, it's going to be bigger than something that it's easier for me to digest. Yeah. So yeah, I'm kind of grouping them into nice groups. The thing that you have to remember is this, and now actually the next thing is this integral test that I guess Connor already knows about. So here's the thing that we need to do for, we have geometric series. We know when geometric series converge or diverge. Then we have the test for divergence. That's the second thing that we need to know about. That tells us whether a series diverges. It does not tell us if the series converges. And then the third thing that we're going to have on this list, and I actually have this list print. I'll make sure that you have a copy of it eventually, but right now I don't want to overwhelm you with all 12 of the different tests that we're going to do. So the third thing is the harmonic series. Harmonic series. The harmonic series, it diverges. Let me write down what the harmonic series looks like. Looks like this. And it's super surprising because you would expect this, because those numbers are so small, you would expect it to converge, but it does not. So this gets us to the next thing. Let me see, I just need to, just for a sec there, should go away. Yeah, there it is. Now, why is this not here? This is not here, just a minute. Wrong PowerPoint. Series part 2, where is my... Thought I had it up. Just a minute. Open. It'll just take a sec here. I'm too lazy to find it now. I'll just write it up here. So this comes to, it's exactly what Connor was hinting at, and that is what's called the integral test. So that's number 4. I know we're blowing through this. Integral test. I think this is the last one we're going to do today because we only have 13 minutes. So the integral test. Let me write it down, and then we'll try it out. So the integral test says this, that if A sub n is monotonic, why can't I write? Monotonic decreasing, then this summation and this integral I'll explain the f of x in a minute. I just realized I should have written one more thing over on the left. Anyway, those two share the same fate. Okay, and this, in this case, f sub n, a sub n, is equal to f of n. So, in other words, you take whatever's here, think of it as a function, and then do that integral. And if that integral converges, then that will converge. If this diverges, that will diverge. Now, it's just a basic sort of description of why this is. You can either consult Connor, or I can draw a picture for you. So here's why this is true. So if you imagine the harmonic series for a minute, the harmonic series is going to be a series of dots on this graph. If I were to graph the harmonic series, so this is going to be 1, this will be 1/2, this is 1/3, 1/4, etc. That if I were to add up those terms, I'm going to get the same thing as if I added up the areas of these rectangles, because each of these rectangles have a base that is 1, and the height is the value of the term there. So anyway, those rectangles, if I add up those rectangles, I'll get an area that is equal to the sum. Notice that if I draw in a curve here, that curve is bigger than all of those rectangles. And the reason why it's bigger than all of those rectangles together, at least if we, here, let's ignore the first rectangle for now because we can't deal with it. So from here over, you're above all of the rectangles. So you're above all those rectangles from there over. And so that means that the integral from 0, from 1 The integral from 1 to infinity of the function will be bigger than the sum where n goes from 2 to infinity. I'll explain in just a minute. Of a sub n. I should have drawn my rectangles different, but this is the way it ended up. So this integral is bigger than these. In other words, if this integral is finite, then when you add up all of these rectangles, ignore the first one, that's why I started 2 instead of 1, then the sum of all of those rectangles will be smaller than this integral. So if this integral is finite, this will be finite. Now let's flip it around to see why they share the same fate. Let's say that instead of drawing my rectangles the way I did, using left, or I guess it was right endpoints, you remember this from your Riemann sum days. Anyway, let's draw them using left endpoints. I'll do it in red here. And you can see that all of these rectangles are bigger than my function value. And so this is just the flip side of this, is that the integral from 1 to infinity of f of x dx will be less than the sum if we start at 1. So any way you cut it, if you're comparing these two, they're going to share the same fate. If this one is finite, then this will be finite. If this one is finite, then that will be finite. So that's good. Well, what if they diverge? Well, if this diverges, this is going to be bigger than that, and that will diverge. And in the same way, if this integral diverges, if it's infinite, then this will be bigger than that. It's divergent. So that's the integral test. Let's go do the integral test with the harmonic series, which is apparently what Connor did. So we're doing this, 1 over n. N goes from 1 to infinity. That will share the same fate as this. So this is all the integral test is. Whoops. 1 over x dx. So notice I've just changed my variable from n to x. So those share the same fate. You can do this. This is easy enough. That's going to equal integral. Oh, I should ask you. You know what this is. Hold on a minute. Where's my next person? I think I'm down here, just a sec, to Mariah. Mariah, what's the antiderivative of 1 over x? Natural log of the absolute value of x, very nice. X goes from 1 to infinity. Of course, we are dealing with only positive numbers here, so natural log of x, same thing. And then, oh, I know, I should do a limit as b approaches infinity, shouldn't I? Limit as b approaches infinity of that. So that's going to be the limit as b approaches infinity of natural log of b minus natural log of 1. We know the natural log of 1 is 0. What is the limit as b approaches infinity of the natural log of b? So what do you think, Max? What is the limit as b approaches infinity of this thing? It is infinity. Yes, very good. So this is infinity, which means that since this one diverges, that is going to taint that one, and that one will diverge as well. So if one of those two diverges, the other one will. By the way, despite the fact that we just did this using the integral test, we're always, when we see a harmonic series, we're just going to say it's harmonic, it diverges. So no sense in doing the integral test if you don't have to. Okay, we need to do the last one before you pack up and leave. The last one was letter D, the sum where n goes from 1 to infinity of 1 over n squared. Hopefully you had a guess. Did you take a guess? Do you think it converges or diverges? Let's find out. What we're going to do is we're going to use the integral test, and the integral test says that either both of these, oh, we should double check. Is this monotonic decreasing? It is, because 1 over 1 is bigger than 1 over 4, which is bigger than 1 over 9, 1 over 16. All of those get smaller and smaller as you go down. Anyway, once you've double checked that, then we'll do this, and let's find a volunteer here. We have Ethan. Ethan, you know the antiderivative of 1 over x squared, don't you? Very nice. So Ethan might have done this like this, or maybe just did it in his head, but 1 over x squared is x to the negative 2, so indeed, you do get negative x to the negative first, and this goes up to b, and it starts at 1. So give me a sec here. I know you probably aren't going to write all of this, because you don't, I know because I was in your seat 39 years ago or so, and I didn't like writing all of this. Negative first minus negative 1. There, we do that. Okay, now let's just finish this up. What is the limit as b approaches infinity of that mess there? So what do you think? What is the limit as b approaches infinity of that? You want me to rewrite it for you? I will.
0.
Oh, yeah, you got it. But just for the rest of the folks at home, let's do it like this. So yes, 1 over b is indeed 0, but don't forget the 1 that I've got tacked on there. So I know I'm trying to rush here, but there it is. So oh, darn it. Sorry. Plus 1. There it is. Okay, that's 1. So because this thing converges, here's the cool thing, is that since this converges, so this converges, it means that this one will converge as well. Now notice that we don't care at this point what it converges to. And by the way, this was a puzzle for mathematicians for quite a few years, decades. And finally, I think it was Euler, Leonhard Euler figured out what the value of this sum was. It's pi squared over 6, interestingly. So when you add up all of those, you get pi squared over 6. But for us, all we care about is does it converge or does it diverge? On your homework, you're going to be asked questions where you're given a series that looks more complicated than this, but you can use the integral test. It'll ask you for the value of the integral, and it'll ask you for does it converge or diverge. You could certainly just guess at that point, but try to think through it and do it right. I'm going to stop the recording now in case you want to come and whisper something in my ear that you don't want everyone else to hear. Otherwise, I hope you have a great day. We'll see you. Oh, I'm going to give you the day off tomorrow, so you'll have extra time to do this homework assignment, all right? So enjoy your day tomorrow.